welcome to True Projects. In this video, we are going to explain about the project, which is an improved YOLOv8 algorithm for rail surface defect detection. Before getting into the execution, first let us understand what is the project about. So you know, right, that railroad industry is keeping expanding more tracks, faster trains, and denser networks where safety really becomes a huge concern. With all that friction and pressure of the trains, with all the friction and the pressure from the trains constantly rolling over the rails, we end up with some serious issues like cracks, scars, and even complicated complete rail breaks. If we don't catch these defects in time, it could lead to major and severe accidents. So now when it comes to detecting these problems, there are some traditional methods that just aren't cutting it anymore. Taking manual inspections, for instance, they can be really subjective and dependent a lot on the inspector's judgment, which can lead to inconsistencies. Then you have techniques like magnetic practical testing and infrared thermography. While they can be useful, they also come with their own set of challenges, like being complex and not always effective at identifying all the different types of defects we might encounter. So there is a clear need for more reliable and efficient way to keep out rail systems safe. And you know that with all the advancements of AI and machine vision, there are now some really impressive neural networks like YOLO. So we have some neural networks like YOLO and faster RCNN that have made a big difference in automated rail defect detection. So these models are faster and also more accurate, which helps to reduce the amount of human oversight needed and ultimately making our rail system safer. But they still face challenges when it comes to the real-time detection. They are all these environmental factors at play like rust, dirt, and changing light conditions that can interfere with these models' ability to detect defects. Plus, defects come in all sorts of shapes and sizes, which adds the another layer of complexity. While the earlier versions of the YOLO have shown some success, they still have their limitations, especially when it comes to the accuracy and also the consistency in detection. This really highlights the need for a more robust solution that can reliably identify defects no matter these conditions. To address the challenges we face in detecting small and densely occluded defects on railroad tracks, we made some significant upgrades to the YOLO V8 model, that is You Only Look Once version 8. So one of the key changes that we have implemented is replacing the original convolutional layers in the backbone with the SPD convolutional blocks. So this adjustment is crucial because it enhances the model's ability to detect smaller and medium-sized defects without compromising the overall structure of the network. Additionally, we also incorporated EMA attention mechanism into the neck component of the model. So this mechanism helps the model to utilize information from different layers more effectively, which ultimately improves how it represents the features. By doing this, we are making sure that the model has better grasp of what it's looking for, leading to more accurate and reliable defect detection. To boost the accuracy of the defect detection, we have decided to switch out the original CIOU laws to the focal SIOU laws. It is that it adjusts the weights of the samples, putting more emphasis on those tricky defects that are hard to classify. This means the model can give precise attention to each detected instance, especially when it encounters challenging cases. So, with these advancements, the system can accurately detect rail defects in real time, even under varying conditions, plus, even manage to keep the model size and efficiency in check, which is really important for maintaining performance without making it too complex. So, to further enhance the detection accuracy, in this project, we have decided to integrate some of the advanced versions of the YOLO model that are YOLO V5X6 and the latest version YOLO V9 as the extension. These updates were really important because they significantly boost our defect detection and also analysis capabilities. By using these newer models, we were able to enhance the accuracy and also the efficiency of our defect identification on the railroad tracks. On top of that, we have built user-friendly framework using this Flask framework. So this makes it easy for users to interact with the system. We also have included secure authentication, which ensures that user interactions are safe and reliable. This way, we can efficiently test and validate the detection results, making the whole process smoother for anyone involved. Moving on to the implementation of the project, we have followed the steps in the flow of work to implement the project. So the first step we have done is we have imported all the necessary libraries and packages that will need for our project. And then we once we have loaded the packages and libraries, we start exploring the dataset. So we load the images from our dataset to understand what we are working with. And then we visualize these images helps us to get a sense of their quality and types of defects we might be detecting. After then, we did image processing. So we have converted the images into blob format, which is suitable for input into our neural network. And then we have defined the classes for our detection. This step is crucial as it determines what type of defects we are looking for. And then we set up bounding boxes, which helps us to identify where in the image the defects are located. And finally, we convert our image into a NumPy array for efficient processing. Next, we loaded our pre-trained model where we examine the layers of the neural network to understand its structure, that is the architecture. Then we focus on extracting the output layers, that we focus on the output layers as these will be essential for making predictions based on our input images. The next step involves some more specific image processing tasks where we have annotated the images that we have did annotation. We combine our images with the respective annotations which provide information about the defects. Since images are often in BGR format, that is blue, green, and red format, we convert them to RGB, that is red, green, and blue format to ensure color accuracy in our processing. Then we create masks for our images, which helps to isolate the regions of the interest for defect detection. Finally, we resize the image to fit the input requirements of the model. So to make the model more robust, we apply some augmentation techniques. So first, we have did randomizing the images. So this step introduces randomness to the images, helping model generalize better. And then we rotate images to simulate different angles of the defect appearances. And we added additional transformations that might include flipping, scaling, and also altering brightness, which enriches our the data set. Then we did installed, we have installed the other packages. So at this point, we ensure that all required packages and dependencies are properly installed and configured in our working environment. Then we prepare our data, especially specifically for the you only look once family of the models. So this involves structuring our data in a way that aligns with how those models process the inputs. With everything in the place, we construct YOLO model architecture. This includes defining layers, activation functions, and configuring the model's parameters. Once the models are built, we train it using the dataset. This process involves feeding the model images and annotations, allowing it to learn to detect and classify the defects. Then, after training, we save the best performing model. This saved model is used for future defect detection tasks without needing to retrain them again. And to make our model user friendly, we have developed front end using Flash framework. This interface allows users to interact with the model seamlessly. And users in the front end, they will be uploading the images they want to analyze for defects on the railroad surface. And once the image is uploaded, we pre-process it in the same way we prepared our training images. So the given image will be pre-processed at the backend. This ensures consistency and accuracy in the detection. With the pre-processed image, we then use our trained model to perform defect detection, identifying any issues present in the uploaded image. So finally, we present the results of the detection back through the front end. This displays allowing users to easily see the identified defects and also understand the model's findings. So this is how we have executed the project. So coming to the algorithms used, these are the algorithms used in the project. So this is the proposed model and these two are the extension models. So these two got the highest mean average precision score than the proposed model. Moving on to the requirements to implement, we need basic hardware and software requirements. So coming to hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, hard disk of 25 GB and above. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, and JavaScript, Bootstrap 4. Now let's execute. To execute, open the code folder which contains source code files. So let's open code folder of the project. These are the source code files in the code folder of a project. Let us understand them. How will they be used in the project? So here in the sample folder, we have some images that we will be using in the front end to test that how are the defects in the images of railroad surface. Coming to static folder, in this folder, it consists of files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. Coming to templates folder, this folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. Coming to this app.py file, this .py file contains the information related to front-end logic of the project. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is the model file which contains the algorithm information. So this will be loaded into the project code during runtime of the application. And here we have notebook file. This file is a Jupyter notebook file which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. And here we have signup.db file. This file is a database file which is used to store the user information. And here in the starting, we have 4 folders in which we have the data set that is used in the project. So let us open this rail surface defects YOLOv8 folder. So here we have 2 subfolders. One is images and the other one is labels. In images, we will be having the images, and in the labels folder, we will be having the files containing annotations or the labels for the objects in the corresponding images in the image folder. So first, let us see in the images folder what are there. So here we have 2 subfolders. One is train and the other one is valid. In train, we will be having the images. So those images we will be using to train the models. And coming to the validation folder, we will be using those images in the validation folder to evaluate how the models have performed. So first, let's see the images in the train folder. So here we have total 560 images of the railway track. So these we will be using to train the model so that they will be able to detect the defects in the railway track. Get back. Coming to the validation folder. So here total we have 558 images in the validation folder. So these we will be using to evaluate the models. Get back. Get back. So let us open the labels folder. Here we also have the train and validation folder. So in the train folder, we have the annotation files which are corresponding to the images of the train folder. Similarly, validation also. Let us open this train folder. So here we have the annotation files which are corresponding to the images in the image folder. So here each file, each label file, it corresponds to an image file in the image folder which provides details about object locations and classes within the image. So let us see, for example, so this first label file, first annotation file, it corresponds to the first image in the train folder. So it corresponds to this image. Similarly, the second image in the train folder of images is correspondent to this validation file. So similarly, for all the 560 annotation files, so these 560 annotation files are correspondent to the 560 images of the train folder. Now let's check with the validation folder. So here we have total 558 annotation files for the 558 images. So here you understood clearly, right? Get back. So these files, these YOLO label files, they follow the YOLO format. So these label files, they often follow the YOLO format where each line represents a detected object. And here each line specifies the object class index followed by its bounding box coordinates, which are normalized to image dimensions. So this is the Object class index. One is one type of class we will be having. Similarly, three different classes. So they are of different indexes. And these are the bounding box coordinates. This is the x limit, this is the y limit, this is the height, and this is the width. Now minimize this. Similarly, we will be having in the same annotation files. To get back. Similarly, in the YOLO V5, YOLO V7, and YOLO V9 folders, we also have the same images, but they are annotated differently because each YOLO version requires its own specific type of image annotation for training and testing and the models effectively. Having separate folders keeps the dataset organized, ensuring that each YOLO version receives the correct annotations it needs to function properly. Now let's copy the path of the code folder from the address bar of the file explorer. So copy the path. Now open the Anaconda prompt. So now using the command cd followed by the space, paste the copied path and now click on enter. This command, it will change current directory to the code folders path. Here, if you observe, current directory is changed to the code folders path. Now we have to compile the app.py file by giving the command python space app.py. Now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. So this is the local host and this is the port. Now we have to copy this local link provided by the Flask framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Paste the link here, click on enter. This is the web page of the project, which is displayed in the browser. And here you can see a registration link, right? So first we need to get registered. So click on that and enter all the registration details if you are registering newly. I have already registered, so I'll directly sign in. So click on sign in. Here we need to provide username and the password. Now click on login. We have logged in successfully and we are redirected to detection page of the project. So here you can see choose file button, right? We need to click on that for uploading the images. So let's click on choose file. So these are the images that we will be using as the test cases in the front end to detect the defects in railway surface. And this is in the samples folder and the code folder of the project. Let us upload the first image. Click on open. Here it is loaded. Now click on upload. The image will be processed at the backend and then we will be getting the prediction. So here if you observe, Rails has been predicted with the blue color bounding box. It's a sea blue color bounding box. And here we have the probability score of 0.64. It's the confidence level that how accurate the detection is. Let us upload one more image. Click on choose file. Let's try uploading this image. Click on open and now click on uploads. It is being processed the backend, so that is why it is taking time. And here we got the prediction. Here it has predicted as brakes. And it is drawn in the green color bounding box and labeled as brakes. And this is the probability score. That is the confidence level that how accurate the detection is in detecting this brakes. Breaks, it refers to the severe fractures or the splits in the rail that can pose significant safety risks. So these defects may occur due to the fatigue, stress from heavy loads or sudden impacts and they require immediate attention to prevent derailments and accidents. So it is very important to mitigate this breaks. Now let's get back. Let us upload one more image. So let's upload this image. Click on open and now click on upload. So here also breaks has been predicted. Now get back. Let us upload one more image. Click on choose file. Let us upload this image. Click on upload. So here if you observe in a white color, creamish color bounding line, scars has been detected and it is labeled as scars with the 0.63 confidence level. Scars on railroad tracks typically refer to the surface irregularities caused by wear, corrosion, or mechanical damage. These defects can compromise the structural integrity of the rail and may lead to further deterioration and if it is not addressed promptly. So it is to be addressed. Get back. Let's upload one more image. So now let's upload this image, click on open, and now click on upload. So here we have three detections. One is scars and light bands, cracks. So first let us understand what is this light bands. And these light bands are detected in the navy blue color bounding box with the 0.60 probability score. Light bands are the areas on the rail surface where a thin layer of material has been removed, often due to grinding or excessive wear. While they may not always pose an immediate threat, they can signal underlying issues and they may lead to more significant effects if not monitored. So they have to be monitored and they have to be addressed. And here, if you observe in the backside of light bands, there is a crack detected. Cracks are the fissures or the splits that develop in the rail due to stress, fatigue, or material defects. These can range from superficial surface cracks to deeper, more dangerous ones that can compromise the rail's strength and integrity, making timely detection and repair crucial for safe rail operations. And here, three are detected total light band cracks and scars. Let's try with one more image. Click on choose file. So let us upload this image. Click on open and now upload it. So here has been detected with the 0.71 probability score. Let's try with one more image. So let's try uploading this image. Image is being processed at the back end. So here the scars has been detected. Let us try with one more image. So let's try uploading this image. So here two defects are detected. One is scars and the other one is light bands. So this is the light bands and here scars is detected. Let's try with one more image. Click on choose file. Let's try uploading this image and now upload it. Here, rails has been detected with the 0.74 probability score. Rails, they come under the category of undulating or wave-like deformations on the rail surface, often caused by thermal expansion or the contraction, heavy loads, or irregularities in the manufacturing process. These defects can affect the smoothness of train travel and potentially lead to safety hazards if they cause excessive vibrations. Get back. Let's upload this image. So here we got the detection breaks. It is drawn in the green color bounding box with a 0.84 probability score. Get back. Now let's check with the graphs. So click on graph. So here we have precision and recall graph of YOLO model. And here each color represents type of class. Here orange is rails, blue, light blue is cracks, red color is the brakes, purple color is the light bands. Similar we have all the other classes. And this is the F1 score graph of YOLO model. And this is the confusion matrix of YOLO. Here we have all the classes. These are the actual values and these are the predicted values. And these are the correct classifications. And this is precision comparison graph. Here on x-axis we have precision score and on y-axis we have all the algorithms used. And here we have recall comparison graph. This is the mean average precision comparison graph. Here on x-axis we have mean average precision and on y-axis we have all the algorithms used in the project. Now let's log out. In this way, just by uploading rail track images to the system, it will detect which type of defect detected in that particular track by using the YOLO models. So this is all about the project.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.